All right, this is AP Calculus AB, and this is the second day of section 5.3. And in this section, if you remember from the last video, we talked about a function, its derivative, and the second derivative, and the relationships between those functions. And what I want to do in this video is just really an extension of what was in the last lesson. And this is really going to focus primarily on understanding how to look at these things graphically, not just interpreting the graphs, but also actually graphing the functions based on the information you know about the function, the derivative, and the second derivative. So that first page with the warm-up, we're going to go through those questions in class. So I'm going to skip into the new material here, which is this first question. It says, answer the following questions about the function, justifying each answer with information obtained from the given graph of f prime. Okay, so we have this graph over here to the right of f prime, and they ask us a bunch of things about it. Now, like I've mentioned previously, whenever I am given a graph like this and it's not labeled, I think it's a really good idea to label what that graph is. So every time we look over at that graph, we remember, we have a visual reminder that this is the graph of the derivative. Okay, so on part A here, it says, on what intervals is the function increasing? Okay, so if I'm going to write the intervals where my function is increasing, that means my derivative has to be positive. And there's actually two ways I could write this answer. So you can see that the derivative is positive between -4 and -2, and then from -2 to 1, we also have positive values. So I can write it as -4 to -2, and also, let's see, -2 to 1. But we could also write it, and I want to show you this because it just depends on what material you're using, what book you're using, what math software you're using, what professor's information you're looking at. Sometimes you'll see those broken apart because technically the derivative is 0 at -2, so the function wouldn't be increasing there. But some people would just combine those together and say that the function is increasing from -4 to 1. And the reason that we would say that is if you looked at the points that were graphed, you could justify that when you're at -2, the points to the right of -2 are above it, and the points to the left of -2 are below it. So it is increasing at that point, even though at that point it has a 0 slope. So you can justify it either way. And I would take either answer, but the main reason I wanted to show you that is if it were a multiple choice question, you might see the answer presented in either one of those forms, and you just treat them as essentially being interchangeable. Okay, B, it says, on what intervals is this graph of the function concave up? So if we're going to look at the original function and we're looking for concavity, remember that means that the derivative is increasing in value. So you can see that our derivative is increasing in value from -2 and then maybe a little to the left of 0. And then it's also increasing in value maybe from 3 to 4. So I'm going to call these intervals -2, and I'm just going to say that's about -1/4. So you can see looking at my derivative graph, it's increasing from left to right on that interval. And then I also have another interval that looks like 3 to 4. Now, one other thing that we've talked about before, but I just want to mention again, whether or not you use an open interval or a closed interval, meaning including the endpoints or excluding the endpoints, it doesn't really make a difference. It's sort of like on part A, where I was mentioning that there's different ways of interpreting these things. It's the same thing with the endpoints. So you can justify including or excluding the endpoints. And so I'll accept either answer. And the main thing I want you to know is when you look at these on a multiple choice, for example, just realize that they might present the answer with a closed interval or an open interval. Okay, so for part C, it says at which x coordinates does the function have local extrema? So you want to sort of think of this as if you were interpreting this from a sign chart, right? On a sign chart, we're looking for a sign change at our critical points. Critical points in this case would be the points where the derivative is 0. So we need the derivative to go from positive to negative or negative to positive. And if that happens, we're going to have an extreme value. So I'm really looking at the interior points here when I'm looking for local extrema. And so I'm just going to look at -2 as a possibility but you can see that the derivative is positive to the left of 2, and it's positive to the left of -2 and positive to the right of -2. So that would not be a max or a min. That would actually be a shelf point. But we do have a sign change here at 1. You can see it goes from positive to negative. So that would actually be a local maximum at x is equal to 1. Now, technically, depending on whether or not we want to include the endpoints, we could classify the endpoints as maximum or minimum values as well. But for the purpose of this question, we're going to leave the endpoints out. We're going to assume that we're just looking at this as an open interval from the standpoint of the local max and the local min. Okay, so now on D, it says, what are the x coordinates of all points of inflection of the graph? Well, points of inflection are going to occur when I have a change in concavity. So concave up to concave down, or concave down to concave up. And remember, concavity is going to be determined by whether my derivative is decreasing in value or increasing in value. And we already talked about this on part B. So we talked about where we have the graph being concave up on that part. So now I can see that from -4 to -2, the derivative was decreasing in value, but then I get to -2 and it starts increasing in value. So since we saw a direction change there, decreasing to increasing, that means the second derivative has changed signs. So that's where we're going to have a point of inflection. And so anytime that derivative changes direction from increasing to decreasing or vice versa, that's all I'm looking at. So about -2, -1/4, and it looks like the other point would be at 3. All right, and then the last part of this, and this is where this kind of gets tough, and this is why we're really doing this stuff on a separate day today. Sketch a possible graph of the function on the interval -4 to 4. So what I'm going to do here is I'm going to create a sign chart so that we can get a good feel for what exactly is happening. So I have, let's see, endpoints at -4 and 4 on this sign chart. But then I also have these points where I have 0 slopes. So -2 and 1. Now, between -4 and -2, you can see that the derivative was positive. Between -2 and 1, the derivative is also positive again. Notice we don't have a sign change here. Remember, that's indicating a shelf point. And then from 1 to 4, now I can see that the function is actually decreasing. Okay, so that's part of what I need to know. Now, the other thing I want to account for is the second derivative. So with the second derivative, I'm going to use my answer from part D to help me create this sign chart. So we said there were points of inflection at -2, -1/4, and 3. So now looking at my graph, I can see that from -4 to -2, my derivative was decreasing in value. And then remember, these are all points of inflection, so I know they're just going to alternate here. So that's going to give me a feel for the concavity of that graph. Concave down, concave up, concave down, and then concave up again. Okay, so now let's try to piece this together. Now, one piece of information that we're missing is, where does this graph have to start? What's a point that this function has to go through? We also don't know any function values in general, so we're going to kind of estimate where these points are, but we're going to use these sign charts and combine them together to get the overall shape of the graph. That's really what we're focused on here. So I'm going to assume that my graph has to go through the point -4, 0. And again, I'm just choosing a point because they didn't give me a point to work from. So that's the point that I'm going to use. And that's why it says sketch a possible graph, because there's really an infinite number of these. Because I could shift that point that I have at 0, I could shift that up or down anywhere, and I would have the same shape, but it's going to change the location of my function. Okay, so now I have to do this really one section at a time. So we can see between -4 and -2, and I'm going to put my endpoints on my second derivative just so we can compare here. Between -4 and -2, you can see my derivative says it's positive. That means my function's increasing. Second derivative is negative. So my function should be increasing and concave down on the interval -4 to -2. Also at -2, I know I'm going to hit a slope of 0. So what I'm going to do here, I'm going to say that my graph has to go through about right there. So increasing and concave down is going to look something like that. Now at -2, I know I hit a 0 slope, But notice the function then starts to increase again. I'm looking at this part of my sign chart. And also from -2 to -1/4, my graph should be concave up. So I know my graph's concave up and increasing until I get to -1/4. Okay, so I'm going to say -1/4 is about, let's see, about right here. And my graph should be increasing and concave up. Okay, so notice I do sort of have a shelf point here. The graph flattened out, got very, very close to a slope of 0. It should be exactly a slope of 0, but I made it flatten out there. Now increasing and concave up. Now on the interval from -1/4 to 1, my graph is still increasing, but now it's concave down. So until I get to 1, I know I'm increasing but concave down. Okay, so I'm going to put my point about right here and make it increasing and concave down. Now I also made it hit a 0 slope there because I can see it's a maximum based on my derivative sign chart. Okay, so the last couple of intervals here, from 1 to 4, my function's going to increase all the way through there. And I also know that from 1 to 4, my graph starts out concave down and switches to concave up when I get to 3. So I'm going to show that it switches here at about 3. I'm going to put a point here. And I'm going to have my graph concave down and decreasing. And then from 3 to 4, it's going to continue to decrease, but then it's going to be concave up. And notice that we have a 0 slope at 4. So it's going to sort of flatten out when I get to that last point. So it's going to look something like this. Okay, so I've sort of created this graph one section at a time. And that's really the main idea in terms of how you're going to do this. You're just going to go piece by piece to create that overall function. Now, the function definitely could have stretched, further up here. It could have gone further down here. We don't have enough information really to go off of yet without combining things that we don't know yet about integrals. So for now, we're just looking for this general shape. Increasing versus decreasing, concave up versus concave down. Okay, so like I said, it's kind of difficult. The more of these you do, the easier it gets. But really what you want to do is break it into a bunch of small pieces and then connect them together. And you can tell you've done it correctly. So when I look at this function that I had above, this derivative function, see how we have a nice smooth graph there. That means my original function should be smooth. It's differentiable everywhere. I should have a nice smooth curve. And yes, obviously I've got some staggered sections where I kind of pieced it together, but if I were to now draw this as one continuous function instead of one section at a time, you can see how it would be essentially a smooth curve. All right, so let's try another one of these. It says if f prime is equal to 4x cubed minus 12x squared, sketch a possible graph for f of x that goes through the origin. So what I want you to do is create your sign chart for your first derivative, create your sign chart for your second derivative, and then try to sketch the graph that would be modeled by that derivative function. And again, notice this one, this time they gave us what we call an anchor point, a point that fixes our function into a location. They told us it has to go through the origin. So go ahead and pause the video, take a few minutes, sketch the graph, and then when you unpause it, I'll show you my solution. Okay, so here's what you should have ended up with, or at least something similar to this. So first of all, I set my derivative equal to 0. I got my critical points, and you can see my sign chart, minus, minus, plus. I have a shelf point at 0, and I have a minimum point at 3. Then my second derivative, I found that. I set it equal to 0 to check for points of inflection. So you can see here's my second derivative. And then these have a multiplicity of 1. So I automatically knew that those were going to be points of inflection. So with my sign chart, I got plus, minus, plus. So concave up, concave down, concave up. And then you can see on my graph here, I just did this one section at a time again. From negative infinity to 0, I can see my graph is decreasing and concave up. And then from 0 to 2, that section, you can see my graph was decreasing and concave down. And then from 2 to 3, I'm still looking at this part of it, 2 to 3, now I should be decreasing still, but now concave up. And then on the last interval, I'm looking at these two, it's increasing and concave up. Okay, so that gives me that general shape. Now, again, how far up or down I go for, this minimum point, that's really to be determined by a little bit more information than what we have to work with right now. Okay, so that's the main idea. Now, you're going to have a lot of these for practice for homework, and that's really what I want you to do. Now, when you have more information you can use, for example, if you know the function, you could use things like a y-intercept, you could use x-intercepts, you can find function values at maximum or minimum points, and you can get a really, really accurate graph. So depending on what you're given, you may or may not be able to get the graph as accurate. So in this case, obviously, I don't have enough information to get those function values, so I had to just kind of guesstimate where those points are going to be. Okay, so down here at the bottom, it said, what if f of 0 is equal to 0, f of 2 is negative 16, and f of 3 is negative 27? Can you write an equation for f of x? Well, the answer is yes. And this is just something that is leading us into something that we're going to do in the second derivative our second semester called an antiderivative. And an antiderivative is just basically taking the opposite of a derivative. And so what we would be trying to do is take this derivative function and figure out, based on that derivative function, what was the original function? Well, that's what I did here was I just said, okay, if I got a derivative term of 4x cubed, that means the original function had to have an x to the fourth there. Or for the second term, if I had a derivative of negative 12x squared, that means my second term had to be negative 4x cubed. So that's really what an antiderivative is. You don't have to know that right now, but I wanted to show it to you because sometimes on these you can actually go back and figure out what the function would look like by thinking about antiderivatives. Now notice I have a plus c here, and that's just because when I take the derivative of a function, I lose all reference to what constant values were there. And the only way we could figure out that constant is if we knew points that the function has to go through. Like, for example, if f of 0 is 0, that means the c value is 0. So depending on the points you have to go through, that's going to fix that c value to be a certain number, and then you would have the actual function that you're trying to graph. Okay, so like I said, antiderivatives, not something you need to know right now, but something we're heading towards down the road. It all sort of connects together. So just wanted to give you a little preview of that. Okay, the rest of what's in this packet is really just practice problems for you. So here I gave you 4 different graphs that I want you to try to create. So I gave you just a quartic function, I gave you a rational function here, I gave you a square root function, and then I gave you one with the graph of the derivative where you're supposed to graph the original function. So I want you to try these on your own. The 3 that you have the function for, you can just use a calculator and check your graphs. For this one, I have provided the answer to you in my completed notes, so you can check that one with the completed notes if you want. And then the last thing in here, there are these practice multiple choice questions. And these are actually questions we're going to go through next block during class because I want to walk you through the steps on the calculator in terms of how to solve these things out. So you can try them on your own if you want. But what I really want to do is walk you through step by step with the calculator during class so that we're really, really clear on what the expectations are for questions like that.